we're getting started with class 22. Our goal is to apply Newton's first law to a variety of situations. So to get us started, here's a scenario. You are standing on a stationary subway car, not holding onto or leaning onto anything. The car abruptly begins to move forward. Describe what happens to you. So this isn't just a subway car, but even just like a regular car. When you start moving, okay, what happens to your body? Hopefully you notice you fall backward or move backward. Okay, particularly in a subway car, you're going to fall backward. Now, you're not actually falling backward. What's actually happening is that the subway car is moving forward, and your body, which is an object at rest, wants to remain at rest. All right. So, we have, let's say, our subway car is like this. All right. That's a terrible subway car. Here's our subway car. Okay. And here's you and the subway car, and the subway car starts to move forward. The reason you fall back is because, well, the subway car, I don't know if I can really select things too easily here. Um, the subway car is moving forward. You see that? How I moved the subway car forward? It's not so much that you are moving back, it's that the subway car is moving forward without you. So naturally, you move to the back of the subway car. All right. Same thing happens here with, let me just unclick that. All right, I want to draw again. All right, so now we're back. Same thing happens if you are standing still on a moving subway car and not holding onto anything. The car abruptly stops. Describe what happens to you. This is like if you're in the car and someone slams on the brakes. You fall forward a little bit or move forward. Fall forward. Okay, pretty sloppy handwriting there. But to kind of just, again, show you what's going on there, let's say you are in a subway car again. You are a body in motion. So let's say the subway car is now moving. You are a body in motion. Your body wants to stay in motion. When the car stops, you are no longer stopping. You are going forward. Oh, headless horseman. Let me try that again. Get the whole thing there. Okay, so you're a body in motion. So when the subway car stops, it stops, but you keep going forward. So you get this feeling like you fell forward. All right. So what happened here in this picture here, pretty good picture here. You'll notice there's like a big center block in the back of the truck, and it hits the front of the truck. It like went through the storage container that's in the back of the truck. So what happened? Well, at one point, the truck and the cinder block and everything were all moving together. Let's say 50 miles an hour. At some point, the truck slammed on the brakes, and the truck stopped because the tires are able to supply enough friction to the truck to stop it. Unfortunately, there was nothing there, or at least not enough frictional force to stop the cinder block from moving forward. So the cinder block, being an object in motion, is going to continue to move in a straight line with constant velocity unless it's acted upon by an outside force. Well, unfortunately, there was not enough force to stop it, and it goes right through the front of the storage container and hits the back of this truck. All right. All right. So let's go through some stuff real quick. Newton's first law: an object at rest will remain at rest, and an object in motion will continue to move in a straight line at constant speed if and only if the net force on the object is zero. We call this the law of inertia. By the way, straight line and constant speed, remember, velocity is when you put speed and direction together. So you could also just say constant velocity here. Inertia is the tendency of an object to resist changes in velocity. I'm freezing up, there we go. Freezing up again. Okay, inertia is the tendency of an object to resist changes in velocity. It is proportional to an object's mass and nothing else. So what do you mean by that? Resist changes in velocity. So a change in velocity, remember, is acceleration, which we know is equal to net force divided by mass. So given any net force, the mass is the only other thing that tells you how, given a net force, excuse me, here's another way to put it, given a net force, the mass is the only thing that will dictate changes in velocity or acceleration. Okay, so the only thing that matters with inertia is mass. So if a 12-kilogram car is moving at a constant speed of a quarter of a meter per second, after the speed of the car is tripled, the inertia of the car will be, well, did the mass change? No. So therefore, the inertia did not change. The velocity does not affect the inertia. The greatest increase in inertia of an object would be produced by increasing the, well, greatest change in mass. So let's look here. It looks like this is our only choice. All right, this one says, is it easier to stop a moving truck or a moving fly? Hopefully, you know it's obvious it's a moving fly, because a moving fly has less mass which again means it has less inertia. Is it easier to start moving a boulder or a feather? Hopefully you know it's a feather. Again, because it has less mass or less inertia. So more inertia means it's harder to move. Less inertia means it's easier to move. Now we're talking about net forces being zero, okay? So another way to phrase a net force being equal to zero is equilibrium, which is a phrase you've definitely spoken about, definitely in at least chemistry class, and probably biology too. Equilibrium. So equilibrium is when the net force equals zero. So that's really important. Equilibrium, I'm going to write this down. That means F net equals 0 newtons. So important. If there is no net force acting on an object, the object, well, let's read what it says up here. If there's no net force on an object, if it's 0, it moves at a constant speed in a straight line. So if there's no net force acting on an object, the object does not experience a change in speed or direction and is in equilibrium. So once an object is moving at a constant velocity, it's in equilibrium. Yeah, a net force, you need a net force to start moving the object. But once it's going, and as long as it's got constant velocity, it's in equilibrium. Even if there's a ton of different forces acting on it, if it's going at a constant velocity, meaning same speed and direction, it's in equilibrium. All the forces are canceling out, whatever those forces are. An object moving at constant velocity has a net force of 0 acting on it. So let's say you are driving down the highway, going 60 miles an hour in a straight line. There are a lot of forces acting on you. There's friction, there's air resistance, there's gravity, there is the force of the road pushing your car upward. There's a lot of forces there. But if you're at constant velocity, all of those forces cancel each other out. All of them. So the net force in that case would be 0 and you would be in equilibrium. So it says here, this question, if a block is in equilibrium, the magnitude of the block's acceleration is, well, looks like we have written over here. Actually, I'm just going to ignore that for a sec. We'll just do it here. So equilibrium means that the net force is 0. And as we've said before, A equals F net over M. So therefore, A equals 0 over M. So A has to be 0. So if we're in equilibrium, not only is the net force 0, but the acceleration is also 0. And if the acceleration is 0, you know that you have constant velocity. And within constant velocity, I know this is a lot here that I'm telling you. Remember, constant velocity means constant speed and direction, not just one. Okay. So equilibrium packs a lot of info into it. If you're in equilibrium, you have a net force of 0 on you. If you're in equilibrium, the acceleration is 0. If you're in equilibrium, you are traveling at constant velocity. If you are in equilibrium, you are traveling at constant speed. If you are in equilibrium, you are traveling at a constant direction or in a constant direction. We have some videos there you could check out. So this is just kind of rehashing things. Simply put, things like to keep doing what they're doing. So an object in a state of rest will tend to remain at rest, and only a force can change that state. So back to the subway car. If you remember when I pulled the tablecloth out from under the plates were analogous to the people on the subway, wanting to remain at rest. The tablecloth was analogous to the subway car moving out from under them. So just again, more info here. Objects in motion. So in the absence of forces, a moving object tends to move in a straight line at constant speed. Now I want to actually fix that. In the absence of a net force. If you toss an object from a space station located in the vacuum of outer space, meaning no air, so no friction, the object's going to move forever, okay, due to its inertia, its tendency to remain or keep its state of motion. Forces are needed to overcome any friction to set an object into motion initially. But once an object's moving in an environment free of any friction, it's going to move in a straight line at constant velocity, or constant speed, rather. You could say constant velocity, that would imply both direction and speed. So let's think about this thought experiment. A force of gravity between Sun and the planets holds the object in orbit around the Sun. If the force of gravity suddenly disappeared, what kind of path would the planet move? Draw on the image below. So you have to know Newton's first law here, and it's a pretty cool thought problem. So Earth is going around, going around, going around. If the Sun were to disappear, there'd be no more force of gravity. Therefore, the Earth must move in a straight line at constant velocity. So if at this one point here, if the Sun just disappeared, the Earth would actually just go in a straight line forever. That's just where it would go. There's no way it could continue to move in a circle without the Sun being there, because to move in a circle, you have to change direction, which means you're changing velocity, which means you're accelerating, which means you need a net force, which would be non-existent without the Sun. If you flip a coin in a high-speed car, it'll come right back down into your hand. Why? Yeah, a lot of people say, like, oh, if I throw a coin up in the air, why doesn't it hit the back windshield of the car? Well, why would it hit the back windshield of the car? If the car is moving 50 miles an hour, you in the car are also moving 50 miles an hour. The coin is also moving 50 miles an hour. If you toss it up into the air, why would it stop moving 50 miles an hour? There's no net force that would stop that. Now, if you were in a convertible and you threw the coin up really high, it might look like it goes way back, because what happens there is once it goes above the windshield of the car, there's a lot of air resistance. That air resistance is a net force, which could stop it. All right. So that is class number 22. Have a great day.